pero como el público son venezolanos, entonces voy a presentar al profesor Rezende en español. Bueno, para mí es un honor hacer esto. El profesor Rezende fue mi profesor. El profesor Rezende, en mi opinión, es uno de los más importantes científicos en el área de ciencia de materiales y nanotecnología en Brasil, probablemente en América Latina. La carrera del profesor Rezende es muy amplia como para decirla toda acá. Voy a resumir algunos aspectos acá. El profesor Rezende es ingeniero electrónico de la Universidad Pontificia Católica en Río de Janeiro. Obtuvo su grado de maestría y PhD en MIT. Es profesor del Departamento de Física de la Universidad Federal de Pernambuco desde el 72 hasta la fecha. Su principal área de investigación es ciencia de materiales, magnetismo y materiales magnéticos, Spintrónica. ¿Ok? Tienen allá unos buenos laboratorios, excelentes. Ha publicado más de 300 artículos científicos. Tiene 3 libros publicados en Springer, en el área de magnetismo y materiales. Más de 8.500 citas. ¿Ok? Finalmente, fue ministro de Ciencia y Tecnología de Brasil entre 2005 y 2010 durante la gestión del presidente Ignacio Lula da Silva. Bueno, Sergio, you can start.
Muchas gracias, Fermin, pela invitação, pela apresentação. Mi espanhol es terrible. Por esta razão, vou fazer a apresentação em inglês. Começar aqui com o share screen. So, this presentation is intended for mainly undergraduate students, physics students. And I'm going to show many slides. So I'm going to, I have to be very fast. More than 1 slide per minute. But since the slides don't have much information, I'm sure that you're going to be able to follow everything. Well, just to show you where I am now in Recife, is the state capital of Pernambuco. Rio de Janeiro and São Paulo and Brazil are here. And we are here at about 5,000 kilometers from Caracas. This is the Amazon. The Amazon is mostly in Brazil, but also in Venezuela, Colombia, and in Peru, as you know well. As Fermin said, we have been working magnetism for 50 years here in Recife. In the year 2000, Fermin was here. We organized the International Conference on Magnetism, which is the main conference in the area of magnetism, and it is held every 3 years in a different country. Let me begin with this slide showing the gross domestic product of the 8 richest countries in the world. The richest one is the United States, as you know, and then China, Japan, Germany, United Kingdom, France, India, Italy. And there is one important point. 70% of the GDP of the industrialized countries are produced in what is called the knowledge economy. In other words, the economy relies on things that are made by human minds, not by commodities. This slide shows the 8 countries with most publications, papers in all areas. And the 8 countries are precisely the same. The 8 countries are precisely the same, 8 richest one. This is not a coincidence. This is because science is the driver of prosperity. It has been like so for centuries. It's not a recent thing. It has been like so for centuries. Now, I show here the 8 countries with the largest number of publications in physics and astronomy. And except for the presence of Russia, Federation here, they are all the same countries I showed before. This means that physics is an area crucial for technology. And that's the motivation for the start. Physics and the technological revolutions that changed the world. Science in Latin means ciencia, science. Knowledge means knowledge. And knowledge is essential for technology. Technology is the application of science. Technology is what produces richness, also feeds back on science, but technology relies on science. In Brazil, possibly in Venezuela, some economists say that our country should not spend money with science. We should invest in technology. There is no way to grasp technology if a country doesn't have good science. And science and technology, they are essential factors for economic development, for the increased wealth of nations, and for the sovereignty of nations. Not a single country can be independent in terms of capacity of making decisions if it doesn't have good science education. Education is essential for science and technology. So what I'm going to do here is to show 6 examples in which developments in scientific developments in physics generated technology that changed the world. This has been going on for 200 years, more actually, 300 years. So I'm going to cover 6 different points. And as I said, I have to show you many slides about this, but this is intended for physics students. Many of the things that I'm going to mention are already known by you. Number 1, electromagnetism, electricity, and light. The birth of electricity becomes arose when Alessandro Volta, the Italian, developed the electric battery. The battery, as the name says, is a battery of different materials. Alessandro Volta discovered that by having specific materials one on top of the other, like here, a potential difference arises between the 2 ends. Actually, there is a potential difference between only 2, but that potential difference is very small. So we need a battery of discs here to have a sizable voltage. Well, the development of the battery made possible the production of electric current. And these 2 gentlemen, Ørsted from Denmark and Ampere from France, independently, they did the following experiment. They passed a current through a wire, and near the wire, they placed a compass, a needle of a compass, and they discovered that the electric current changed the direction of the needle, indicating at that time they did not know what this was, indicating that the current creates a magnetic field. They also discovered that if they put a second wire with a current near the first one, there is a force either separating or attracting the two wires depending on the sense of the current. And the conversion of electricity into a force means the conversion of electric energy into mechanical energy. And this discovery immediately led to the first technological application. The electric motor in which we apply a current and the thing rotates was produced a few years before Ørsted and Ampere discovered. This is a photo of a modern water pump. And as you know, we have electric motors all around us, in the computers, in the refrigerators, in our homes, the cars, everywhere. Well, immediately, the scientists, the physicists, began to look for the reciprocal effect of that one. And the Michael Faraday, the British, and the American, Joseph Henry, they discovered independently that if they move a magnet close to an electric circuit like this, the motion of the magnet results in an electric current. In other words, you know well that what produces the current is the variation of the flux, of the magnetic flux. This is the reciprocal effect of the previous one, and it allows one to convert mechanical energy into electric energy. This discovery actually produced a big revolution worldwide. This revolution, well, of course, with this discovery, in a few years, some engineers were able to produce, to build an electric generator. The electric generator is the device that converts motion into electricity. As you know, there is a rotor here, a winding in the rotor, and as the rotor rotates, there is a change in the magnetic flux, there is a generation of a current. An independent discovery, which did not involve much science, was very important for the revolutions that took place. Thomas Edison, the American discoverer, he was a very able person. Over his life, he had over 2,000 patents, and he created a company called Edison Electric that then became the General Electric, a very important company, as you know. Well, what Edison did was to pass a current through a filament in vacuum so that it would not undergo combustion, and this produced light. In other words, current can produce light, and since we have generators, and the generators produce current, voltage, electric energy, this is transmitted at a distance and distributed to industries, to towns, to houses, homes, and used for pumping water. All of these devices here have an electric material. I'm going to speak very briefly about electric materials. There's electric material here, magnetic material, I mean, magnetic material in transformers, magnetic material in the water pump, in industry, and at our homes. And the electric energy and lightning revolutionized the costumes of humanity. This is a photograph made with several photographs by satellites showing the illumination of the world. And this is a good representation of the richness of the world. The richest parts of the world are the center east of the United States, Western Europe, Japan is here, the coast of Brazil, Venezuela is here. But you see that in Latin America, richness is concentrated in the coast, which is a difficulty for us, as you know. Well, number two, development, electromagnetic waves, electronics, and communications. At the end of the 19th century, the British James Clerk Maxwell, which was a brilliant theoretician, he started with the developments made by Einstein, Ampere, Faraday, and Henry, and he wrote these equations. This equation here represents the induction. A change in magnetic field produces an electric field. And this is Ampere's law. Current produces a magnetic field. And then there are the other relations that you know. And Maxwell postulated the existence of this term so that there would be some symmetry between the two. But from these equations, Maxwell was able to obtain a wave equation. And then he predicted electromagnetic waves. And he said that light was an electromagnetic wave. Many physicists did not agree with Maxwell. They thought, this is a crazy guy. There is no such a thing. But a German, Heinrich Rudolf Hertz, believed in Maxwell, and he made a very ingenious experiment to demonstrate the existence of electromagnetic waves. He had a circuit with a spark gap here, and here two wires connecting to a coil. The coil produces a large voltage. The voltage produces a spark in the gap, and this very fast current produces a wave, and he detects the wave in the other ring here. So this was a demonstration that electromagnetic waves existed. And then this other brilliant engineer, Guglielmo Marconi, he used electromagnetic waves, and then they were called Hertzian waves because they were demonstrated by Hertz, to use to transmit telegraphy with no wire. Wireless telegraphy was demonstrated by Marconi in 1894. In 1901, Marconi made the first overseas transmission of Morse code, which is used for telegraphy. And he got the Nobel Prize in Physics. See, Marconi did not prove anything in physics, but he used physics for a very important development for telegraphy. And in 1910, he obtained the Nobel Prize in Physics. Well, at that time, engineers, technicians, physicists were trying to develop communication at a distance. And the American Lee Forest invented the trial tube. In the trial, electrons are emitted by the cathode. They go through a grid in which a voltage controls the flux of electrons, and then they are captured by the anode. And And this trial tube allowed amplification. With the trial tube, Marconi and then a Brazilian, Landel de Moura, achieved signal transmission at a distance, and another American developed the radio receiver, and then we started having radio communication. People began to receive live news by voice, also music, of course, by radio. This produced a big revolution in the world. Young people cannot think of a world without internet, without iPhone, tablets, and so on. Well, the radio receiver was developed only 100 years ago. Only 100 years ago, we had no way to communicate at a distance. Development number 3, the understanding of the atom. And this has had several steps, as you know. In 1900, Max Planck, another brilliant German physicist, postulated, he was a theoretician, and he was intrigued by the experiments involving blackbody radiation. He postulated that the oscillators, that the heat in the material had to do with the vibration of particles. He didn't know what it was. And this vibration was quantized. In other words, the minimum energy of the oscillator was proportional to the frequency, and the proportionality coefficient was a constant, a universal constant, was later called Planck's constant. He received the Nobel Prize in 1980 for recognition for the service he rendered in the advancement of physics and the energy quantum. Then another brilliant, the most brilliant one, German, Albert Einstein, postulated without any evidence, any experiment, that, well, since oscillators are quantized, light is also quantized, and light consists of energy packets that he called photons. A few years later, an American, Robert Millikan, made an experiment in which a cathode is illuminated with some light, and he discovered that the light induced the emission of electrons. And this was called the photoelectric effect. And he discovered that there was a minimum voltage necessary for this, and he measured this voltage as a function of the frequency, and the voltage, the retardation voltage, is proportional to the frequency. Well, this was a demonstration of Einstein theory, and Einstein received the Nobel Prize in 1921 for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. Millikan received the Nobel Prize 2 years later for his work on the elementary charge of electricity and on the photoelectric effect. Millikan and Einstein became good friends. Einstein had moved to Princeton University, and Millikan was at Stanford, and they met frequently. Here, it's a photo in which they went in a ship to make astronomical observations. Well, developments continue to be made. 1915, Niels Bohr, another physicist from Denmark, postulated another quantization. Physicists were intrigued by the discrete nature of the emission in hydrogen, and then the discrete spectrum was explained by Bohr, that postulated that the motion of the electrons around the nucleus was quantized. And the quantization was made in the angular momentum. So the orbitals were discrete. And when an electron went from one allowed orbit to another one, it emitted photons with discrete frequency. Bohr received the Nobel Prize and became one of the most important scientists of his time for his service in the investigation of the structure of atoms and of the radiation pattern. And then finally, 1925, quantum mechanics came into the stage. As you know, Heisenberg in Germany, Schrödinger also in Germany, but he was Austrian. They developed a consistent theory for quantum mechanics. This is Schrödinger equation. Heisenberg formulation was a little different, but with the quantum mechanics, they could explain the atom. The atom then the electron is characterized by wave functions. The wave functions are discrete. They have discrete energies, angular momentum, and so on. And this really produced a big revolution. The fact is that in the middle of the 20th century, the electromagnetic spectrum was completely understood. From radio, frequencies used in radio waves, to all the way to X-ray, later to gamma rays. And quantum physics, as you know, has many applications. I'm going to show a few of them in the next three topics. First is semiconductors, transistors, materials for electronics. Well, quantum mechanics explains the atom, and then he explains materials, which are made of atoms. And with quantum mechanics, one can study and calculate properties of insulators, metals, semiconductors, organic materials. And the properties are many: electronic, optical, dielectric, magnetic, thermal, and so on. And first with semiconductors. The vacuum tubes that I mentioned, they were very important for developing electronics, but they were very cumbersome because the vacuum tube was big, consumed a lot of heat, needed high current to operate. And then physicists began to look for a device to replace the vacuum tube. And in December 1947, 74 years ago, these three Americans, Shockley, Bardier, and Bertrand, announced that the Bell Telephone Laboratory, which was the most important research laboratory in the world at that time, they announced a device which they called transistor. And this is the photograph of the first transistor. This is how things are done in the laboratory. This is a plexiglass structure. This here is a germanium slab. And two contacts are made here. One for the emitter, one for the collector, and the base is here. What they showed was that if they passed a current through here, another could control the first one. So the control of a current by another current is what makes possible amplification, switching, and so on. These three brilliant physicists received the Nobel Prize in 1956. And this is a representation of a transistor. As I said, it has an emitter, a base, a collector. Electrons or holes are emitted by the emitter. They go to the collector, and they are controlled by a current in the base. this is a photo of an actual transistor, as you can see in circuits today, or you can buy in the store. And this is a photo of the first portable radio. The first portable radio was made by 5 or 6 transistors, and people then were able to listen to radio with no wire connecting to the wall. This was a big revolution. You cannot imagine how important this was in the 60s, 50s, 50. Well, 10 years later, another American, an engineer, Jack Kilby, developed the integrated circuit. The integrated circuit is made of many components, semiconductors, metallics, and so on. Here is one integrated circuit. And in this wafer, we have hundreds of electric integrated circuit, which is called chip, integrated circuit, or IC, or chip. And here's a big figure that shows the number of transistors per die that people were able to make, to manufacture along the years. And as you see, this is a logarithm scale. And the increase was very fast. Every 18 months, there was a doubling in the number of transistors. And this made possible current technology. Here is the 4G technology that we use today. And the chip revolutionized electronics. Kilby got the number one. Application of chips in electronics, many, as you know, in computers, in tablets, and so on and so forth, and in equipment for applications in all areas. Well, magnetism is also important for technology. As you know, beside the electric charge, electrons have spin. And the spin is associated with the magnetic moment. So since atoms have electrons, they can also have spin and magnetic moment, as long as the spins do not cancel. If there is a net spin, a material can be formed by atoms that behave like magnetic needles, atomic magnetic moments. And magnetic materials have applications. Most applications are still classic, conventional applications. Soft magnetic materials are materials that have a very narrow hysteresis cycles, and they are used in transformers, in motors. Hard magnets, which are materials that have a hysteresis cycles very broad and very high, they are used in generators, in motors, in magnets, in microphones, and so on. Intermediate materials are used in magnetic recording. That means that if we apply a magnetic field to a material, we magnetize the material, and then when we remove the field, magnetization remains. But we can actually demagnetize and record another information. So if the magnetization remains, that means that we can store information. And magnetic recording is a technology that has evolved over the decades. And in recent years, magnetic recording had a big development made possible by Spintronics. I don't have much time to talk about Spintronics, but this is the area of physics and technology that make use of the electron spin to perform new functionality. And we usually use, we have to use multi-layers nanostructures, which are made of several layers of materials with very small thickness, few nanometers, with only a few atomic layers, and with magnetic materials intercalated by non-magnetic materials. Well, in 1988, the French group announced the discovery of the giant magnetoresistance. Actually, the first author of this paper is a Brazilian. He's a Brazilian professor in Porto Alegre, Rio Grande do Sul. He was a postdoc of Albert Fert. Fert was the leader of the group. They discovered that in a multi-layer, if they measure the resistance, and if they apply a magnetic field, there's a large variation of the resistance. And they call this giant magnetoresistance. The giant magnetoresistance makes possible a spin valve, which is made of the following. This is a ferromagnetic material in which the magnetization is pinned by the magnetization in antiferromagnetic material. This is a conducting layer, non-magnetic, like copper, and this is another magnetic layer. Well, and this is free to change, to rotate. If the magnetization here is in this direction, parallel to this one, this layer has a small resistance. Now, if the magnetization is opposite to the reference layer, the resistance is high. So by changing the direction of the magnetization, one changes the resistance. So one changes a voltage that is produced by the current. And this is used as this sensing layer for magnetic recording. Because the traditional magnetic recording was read by the Faraday effect. But the Faraday effect requires large area because it requires flux. And this spin valve sensor is very sensitive to magnetic field, not to flux. And the introduction of magnetoresistance had made possible a very big increase in the areal density shown here in the log scale. So this made possible the decrease in the size of the bit and the increase in the memory capacity. Albert Fert and the German Peter Greenberg, who discovered the GMR independent from Fert, they received the Physics Nobel Prize in 2007. Well, the last revolution, laser, that is made possible by the interaction of radiation with matter. To understand this, consider a system with just two levels. We have an electron in the upper level. If the electron decays spontaneously to the lower level, it emits a photon with an energy proportional to the energy difference. If the electron is in ground state and it absorbs a photon, it can go to the upper state. And so if we have an electron in the upper state and a photon comes, the electron will undergo a transition to the lower level and it will emit photon. This is called stimulated emission. Stimulated emission because the emission is stimulated by an incoming photon. This is the main phenomenon involved in laser. If we have a system with many atoms and the system is in thermal equilibrium, most atoms are in the ground state. But then if photons come, electrons in the ground state will go to the upper state and the system absorbs energy. The energy is proportional to the photon frequency and to the difference in the population of the two levels. Now, if we have more electrons in the upper level, and then a photon comes, there will be emission of more photons. A system in which there are more electrons in the upper level is called a system with population inversion. Population inversion is what makes possible the operation of lasers. Notice that in this case, the absorbed power is negative. Absorbed power negative means emission of power. Well, actually, this was known for several decades. It had been predicted by Einstein. And it took 30 years for physicists to be able to use this phenomenon for amplification of light. Actually, the first device was not amplification of light, it was the amplification of microwaves. And this was achieved by Charles Townes. And a laser or a maser needs an active medium for the stimulated emission of radiation. It has a pumping mechanism to produce the population inversion. And also, usually, it needs a resonant cavity with partial output of the radiation. Some lasers don't need a cavity, but most do need a cavity. As I said, stimulated emission was predicted by Einstein. Well, the development of the laser also was done in the Soviet Union, and two Soviet physicists, Bazov and Prokhorov, together with Townes, they received the Physics Nobel Prize for the great invention that really revolutionized technology. Well, there are many types of lasers, gas lasers, solid lasers. But the most important laser is the semiconductor diode. A diode, as you know, is a device that consists of N-type region together with a P-type region. If we apply a voltage, electrons in the N-type move towards the transition region, and holes move here, and electrons and holes in this region, they recombine and they emit photons. Any recombination produces photons. This is a schematics of a simple light-emitting diode. The light-emitting diode is made of a p-n junction, and as we pass a current here, light is emitted, so the junction needs to have an opening here, an opening for light to come on. This is the symbol of the LED. So in a LED, we pass a current, and light is emitted. The inverse phenomena is what makes possible a solar cell. Electric photons are incident on the solar cell, result in an electric current. And here I have to make a commercial. Fermin said that I have a few books. This is a book which was published by a Brazilian publisher, Materials and Electronic Devices. And then last year, actually this year, I worked in the translation, updating of the book, and it was published by Springer this year, Introduction to Electronic Material Device. This book is designed for undergraduate courses for electrical engineering and physicists students. Well, the semiconductor diode laser continued to be developed. The Russian Alfanov and the German Krummer, they proposed that instead of using just a p-n junction, one should use a heterostructure. A heterostructure means, as the name says, a structure made of different materials. The idea is that electrons in the conduction Then we actually go to this intermediate region, and the area in which they can recombine is much larger than in a single junction. And the development of heterostructural laser made possible very efficient diodes and lasers. They received the Nobel Prize in 2000 for developing the semiconductor heterostructure using high speed in optoelectronics. Now, this is a scheme of the semiconductor laser. As the current increases above a threshold value, the power emitted increases a lot and the light becomes coherent. And the diode laser is essential for optical communication. They revolutionize communication by making possible a communication by means of a fiber optics, and this is essential for communication, also very much used in medicine and industry. So the optical communication, here's a scheme. I have to go fast. But the fact is that during the 70s, commercial labs were in diode laser operated only in the infrared and the red regions. But they had applications. Here are the several forms that LEDs are made. They are used in displays of different types, different things. And later, the green LED was developed, but we did not have a blue LED until a few years ago. And as Newton discovered centuries ago, white light is made of three basic colors, like red, green, and blue. And the blue laser was missing for many applications. And then Suji Nakamura, Japanese and other Japanese, that I'll show later, they developed a blue LED. For this, they discovered that gallium nitride that has an energy band in the blue region could be used for making a heterostructure that produced photo emission in the blue region. Well, the blue LED made possible efficient light with all colors, and then also lamps. A blue LED can emit in the ultraviolet, blue to the ultraviolet, and then if this light is used in a phosphor, phosphor is a material that produces light when stimulated somehow. The fact is that the blue light with this wavelength, 465 nanometer, of the LED excites the phosphor layer of the egg with serum in the bulb, and this emits lights in the range, the visible range. So until some time ago, we only had incandescent lamps invented by Edison. And an incandescent lamp to produce 1600 lumens, which is the unit of light, needs 100 watts of electric power. Then fluorescence light came, much more efficient. But then the LED light comes. Today we buy LED lamps with very good price, and we can produce the same light as the incandescent light with 10 times less power. Today we have lamps with 1600 lumen that requires 10 watt electric power. And this is a big saving, considering that lighting is very important for humanity. If we can use 10 times less power, that means a big saving. Well, Akazaki, Amano, the two other Japanese that I mentioned, and Nakamura received the Physics Nobel Prize in 2014. Look at this citation. This invention was important not only for physics, but because the invention of the blue lathe made possible the fabrication of LED lamps, and the LED lamps are much more economical, as I said, and this is important for the serious problem that we have today of the climate change. So new light to illuminate the world. With this, I finished this talk, and I'd like to show you our group in Recife. This photo is a little old, but this is my colleague, Antonio Azevedo. That's myself, Fernando Machado. Roberto Rodriguez Suarez is a Cuban who is a professor in Chile, and several students and postdocs. And I thank you very much for your attention, and good luck to all of you. Thank you.
Thank you, Sergio. Muito obrigado. Okay, let's now start with the session of questions. ¿Alguna pregunta para el profesor? Any question? Any question? Diego.
First of all, thank you very much for the presentation. It's been really beautiful and it's interesting at the same time. So my questions are the following. Let me look for them because I wrote them out. First, if you had to choose one of the inventions shown and explained today, in your opinion, which one would be the most important?
Diego,
And the second, continue.
Let me answer this one. It's very difficult to say which is the most important, because each one came in a different time.
Mm-hmm.
That time, they really produced a revolution. The first one, the simple one, the Ørsted and Faraday, the conversion of electricity to motion and vice versa. This produced an enormous revolution in industry, in all customers, and so on. So each one has a different perspective. Of course, the revolution caused by the semiconductors and the magnetic materials and the laser would not be possible without the development of quantum mechanics. So the development of quantum mechanics perhaps is the one that produced the change that we have been seeing for almost 1 century. Well, for 70 years. For 70 years, we have been seeing development which would not be possible without the development of quantum mechanics. And of course, while quantum mechanics was being developed, some people, economists and society, thought that, oh, these physicists, they are crazy. They keep thinking on things that do not exist. But the things that they discovered were essential for the revolution. But the answer, direct answer to your question, that I'm not able to point to the most important. They are all very important, and they came at different times.
Don't worry. Rather, thank you very much for your answer. And the next question is this. You know that energy's definition is a trivial topic which will not have an end for now. However, could you define for us what energy is in your own words?
we people, we live and we operate because we have energy, and we need to be fed by different types of food or elements that have energy. Now, to have food with energy for our life, many types of energies are needed. The industry that produces the food needs energy. The energy, the growth of the plants is made possible by the energy that comes from the sun. So energy is essential for life. And what's been going on is this, as energy becomes more scarce, more difficult to produce, scientists have to find new ways to produce energy because energy is essential for life.
Okay, thank you very much for answering my questions. And thank you for today's presentation.
Thank you, Diego, for your questions.
¿Alguna otra pregunta? Another question?
I have
una pregunta en el chat.
I have a question. Fermin, my question is, where all these students are? Are they in a single institution or this?
Many.
Many institutions, all in
Yes.
Venezuela?
Yes, from federal universities.
And this program is a program that was created during the pandemics, or you had it before?
No, it's the first time, sponsored by ICTP and Physics Without Frontiers.
When was this Physics Without Frontiers created?
Ana Maria.
Yeah, I'm not sure. I think about maybe 6 or 7 years ago at ICTP. They have been now sponsoring projects for several years all over the world. Yeah, all over the world. And
Okay.
yeah, they promote mostly educational activities. Yes.
Thank you.
Yeah, Professor Rezende, there is a question here in the chat. I mean, we have very poor internet connection in Venezuela, so the students, it's difficult for them to open the microphone, so they write the questions in the chat.
Yes.
And here, I think you were asking also, the students are from many universities. I think this question is from Giuseppe Scolamiero. I think he's from Universidad de Carabobo. And he asks, which areas in physics do you think will be more relevant in the next few decades?
Could you repeat the name of the student, please?
Scolamiero.
Scolamiero. This is a difficult question. As you know, physics has many areas. 70 years ago, when the semiconductors were being developed, the most important area was particle physics and nuclear physics, because the development of the atom, the understanding of the atom, led physicists to go deep into the atom, into the nucleus, and the constituents of the atom were not well known. So this area was very important. Theoretically, and gradually, people started using big machines to make experiments with atoms. Now, with the development of the semiconductors and then the lasers, the physics of materials, solid-state physics, then the name changed to condensed matter physics, became very important. And today, around 50% of the physicists worldwide work in condensed matter physics. Now, condensed matter physics also gradually became more sophisticated. And as it becomes sophisticated, it becomes more interdisciplinary. And then there is a strong interaction between some areas in chemistry with condensed matter physics, and gradually a very important interaction with biology. So the understanding of biological elements is still a big challenge. So my answer is that not a single area in physics will be the most important. Interdisciplinary areas will become gradually more and more important. But condensed matter, in a way, is the largest areas of research in physics.
There is another question for you, Sergio, in the chat from Mariana. Mariana wants to know what, in your opinion, do you consider there is an upcoming technological revolution?
Mariana, this is a very difficult question, very difficult. As you know, a country that has been developing very fast is China. China has a big population. It has a very strong political regime. And for a few decades, China invested in educating its population. And then as the population was educated, working better and so on, China started investing in science. And for this reason, China is today developing technologies at the same pace as the United States and Europe, like the 5G technology. China last year produced a plan for development until 2050, another for the next 30 years. And China is investing, in China is, in this document, says that we will be undergoing new revolutions in the next decade. So, of course, now that we have all of these digital communication, all these equipments that we have, we can think that a very important thing that will happen is that with the development of materials and devices, the technology will become faster and faster. So what we have now, that in some places the communication, the speed of communication is low. We cannot see actually the images very fast. This will be one of the most important things. Communication will become faster in all respects, almost instantaneous. And instantaneous communication in which we can carry at any time, we will be able to use a small phone or a watch, even a watch, and communication instantaneously with anyone, anywhere in the world. This is the goal of digital communication. And for this to happen, we will need more developments in materials and devices.
Sergio, there is a comment from Diego. We like hard questions. That's a comment for you.
Okay.
They like hard questions.
Yeah. Thank you. Thank you. That's people. Well, good questions are hard questions.
Ana, no sé si hay chance para alguna otra intervención.
Sí, sí, claro. Sí, si hay alguna otra pregunta, aprovechen
¿Alguna otra
ahora al
pregunta?
profesor Rezende.
There is no more hard questions.
Okay, Fermin, José Fermin, thank you.
Muito obrigado, Sergio, pela sua palestra.
Muchas gracias.
Muchas gracias, profesor Rezende, a nombre de todos los organizadores y de los estudiantes. Todos le están dando las gracias por el chat.
Muchas gracias, Ana María, José Fermin. Hasta la vista.
Estaba el profesor Landines también en la audiencia.
Ah, está Landines, Sergio.
Bueno, Landines, ¿cómo está?
David Landines. Ficou mudo.
No, quizás ya se fue.
Ah. Tá bom, Sérgio. A gente fica em contato.
Isso mesmo, vamos manter contato, Fermin. Quando pudermos, vamos nos ver presencialmente, ou na Venezuela ou em Brasil.
Eu prefiro a segunda. Eu prefiro a segunda.
Profesor Rezende, le voy a enviar un enlace para que por favor nos envíe el PDF de la charla.
Perfeito, Ana Maria. Vou
Sí,
mandar.
perfecto.
Não posso mandar o PowerPoint porque é muito grande, mas o PDF eu vou mandar ainda hoje.
Sí, está bien.
Tá bem, até mais, até a próxima.
Está
Até
bien.
mais, Sérgio. Obrigado.
Obrigada. Hasta luego.
Hasta luego.
Sí, a todos los estudiantes nos vemos a las 11 para la visita virtual a Atlas. ¿Sí?
A las 2 hay otra conferencia, ¿no?
Y luego a las
Bien.
2 hay otra conferencia. Sí,
Ok. Entonces, ahí nos veremos.
sí, nos
Bueno,
vemos.
gracias a todos. Que tengan feliz día.
Hasta luego.